Hey there, and welcome to your first lesson on higher level mathematics. Um, right, so we're beginning with numbers today, number theory in particular. So let's take a look at the lesson plan for today. So we're beginning with place values. So starting at the beginning, just looking at, how we actually construct numbers in the first place, and then how we can use that in long arithmetic when we're trying to do arithmetic with very large numbers. Then we can move on to things like indices and roots, which are when you take a power, an exponent of a number. You might not have seen that. We'll look how that works. And then how we can use that in standard form, which is how we basically deal with really big or really small numbers, how we can write them in a more concise way. And we'll finish up on order of operations. So that's when we've got many operations going on all at once. What order we do them to make sure we get the right answer. So let's take a look at place values first. So going right to the very beginning here, how do we actually make numbers? So we have a base 10 count system. So we have 10 digits like this. We count from 0 up to 9. Okay, how do we then continue counting from there? We reset the 9 to 0, put a 1 next to it. So that 1 carries over into the next column. So that next column is now, it's not ones, it's tens. And we can continue doing it like this. So we're now getting two lots of 10 and all the way up until we get nine lots of 10. So then we have 99. What do we do then? Same thing again. We reset the zeros and carry the one over. So now we're in the hundreds column and so on and so forth like this. And this is how we just construct numbers. So we take a look at a number like this and we want to read what this is. And like I said, each number in each column represents something different. So this is a 2, so 2 units. This one here is not an A, it's actually 80 because it's in the tens column. That 7 is 700 because it's in the hundreds column, and so on and so forth. We've got thousands, we've got tens of thousands, hundreds of thousands, and then finally millions. And you see here, every 3 digits from the right, we put a little comma down, and often just makes large numbers easier to read. So this one we can read as 1,045,782. Right, so let's move on to long arithmetic. So this idea of, place values and, carrying things over from one column to next, we use that in long arithmetic. So something like this, we take two numbers that we're trying to add together, not particularly big numbers here, this is just for, demonstration. So we can then just add down the place value. So we have 2 plus 4 here is going to get us 6. And then similarly, we can do 5 plus the 6, which gets us 11. Now you see that 1, like the tens, what would be the tens, if you're adding 5 and 6, is spilled over to the next column. So what we do is we put that there like that. And when we then add down the next column, 3 plus 1, we add an extra 1. So we get 5. And so you could imagine doing that for a really big number. You just continue down all the place values, and it can make adding very large numbers a lot easier. So let's try this again with, say, subtraction. Well, slightly different. So here we can do the same thing again. We do 2 minus 2, it's fine. But the next column, you see, we're doing 1 minus 3, which is a bit of a problem because that's going to go negative. So what we do is we borrow 1 from the next column. So that 1 at the top is going to be 1, 1, which is 11. So 11 minus 3, we get 8. And we put a little minus 1 there so that we know we've borrowed 1 from that column. So now we have to do 4 minus 3 minus an extra 1. And that's just going to come out to 0. So you see the answer here is 80. We don't really have to put that 0 there because it's not going to change the number at all. So a little aside for when we're adding or subtracting negative numbers. So I've shown it a few examples here. The easy way to remember it is if we're doing a plus, a negative, or minus a positive, it's going to become negative. So if the signs are different, it becomes negative, and if the signs are the same, then it's going to be positive. So you see when we have 5 minus 3, it actually becomes 5 plus 3 and becomes 8. And I like to think this just in terms of like financial terms. So you can imagine like a negative number as being a debt. So say if I had £5 and then I add a debt of £3, which is like minus 3, it's like you're losing £3. And so it makes sense that would become 5 minus 3. And similarly, if I subtract a negative number, it's like I'm removing a debt. If I had a debt of £3 and then it gets removed away, it's like I've now just gained £3. So 5 minus 3 becomes 8. So that's kind of the way to think of it. So you don't have to just memorize rules. Um, we get a similar thing with multiplication and division. If the signs are different, it's going to be negative. If the signs are the same, it's going to be positive. So normally when I'm doing these kind of things, I'll just ignore the signs. Like say if I did 6 times minus 2, I'll just do 6 times 2 first, which is 12, and then look at the signs. We've got a positive and a negative. I know that becomes negative, so I'll put negative 12, and so on. Right. So let's see how we do long multiplication now. So this here, we have to just go through each digit individually. So we tend to set it up like this with the bigger number on top. And again, line up your place values. And we'll look at the first digit here being 3. And we multiply that through all the numbers on the top. So we do 3 times 2 is 6. 3 times 4 is 12. And you see it spilled over. So we carry that 1 there. 3 times 1 plus the 1 gets 4. So now we do the same thing for the next digit, but remember, because that's in the tens column, it's not a 5, it's a 50. And that's important when it comes to multiplication. So what we do is we put a 0 here because we've got that extra factor of 10. Multiplying by 10 is essentially the same thing as putting a 0 on the end of the number. You'll see what that is in a sec if you're not sure. And then from here, we can just carry on as usual. So we do 5 times the 2, which is 10. We're carrying the 1, so we do 5 times the 4, which is 20, plus the 1 gets 21. And the 2 is carrying over again. We do 5 times the 1 is 5, plus 2 gets us 7. And then from here, we can just add these up in the same way we did a moment ago by adding down the place values. And the reason why we're doing that is because that first number, you can see that it's essentially 3 times 142. And the second number is basically 50 times 142. And you add them two together, you're going to get 53 lots of 142, which is exactly what we want. And if we had a bigger number we was multiplying by, then we just essentially do the same thing again. So if we was now timesing through with a hundredths digit, we'd have to just put down 2 zeros first and carry on. Because you've got that factor of 100, which is the same thing as having 2 zeros at the end. So finally, let's wrap this up with division. So this is how we represent division. It looks very similar to a square root if you're familiar with what a square root is, but it's not the same thing. This is 273 divided by 7. And how we do this, we start from the left of that big number, 273, and we try and divide digits. So we try and do 2 divided by 7. We can't do that because 2 is less than 7. So we do 27 divided by 7. And we can get 3 lots of 7 in there. That gets us to 21, but we have a remainder of 6. So we put that 6 down there. And again, we can't do the 6 divided by 7. So we bring down the 3 and we do 63 divided by 7, which is 9. And we get a remainder of 0. So once we get to the end like that, with a remainder of 0, we know we're done and we've divided this completely. And the answer is 39. But we won't always get a whole number here. So say if we did the same thing again here with a 4, do 27 divided by 4, we can get 6 lots of 4 in with a remainder of 3. Then we bring down the 3 and we do it again and we'll get 8 with a remainder of 1 because 4 times 8 is 32. And then we've got to the end and we've still got this remainder of 1. So the answer would be 68 remainder 1. But if we wanted just one decimal number, what we could do is extend the digits along like this because 273.00 is the same thing as 273. Like those zeros don't make a difference. But what they do allow us to do here is we can bring the 0 down and carry on the division. So we do 10 divided by 4 is 2 with a remainder of 2. Bring down another 0. 20 divided by 4 is 5 with a remainder of 0. So we can keep going on as long as we need to in order to finish the division, where it'll get to something like this, where you get a remainder of 0, or what you'll find is it will start to repeat. And this will always, one of those two things will always happen when you're dividing two numbers. Right, so that's enough for long arithmetic. Let's move on to laws of indices. So indices is basically when we're dealing with powers. And say something like this, like 2 to the power 5. And it's like, first of all, what does that even mean? Well, let's look at, say, 2 times 5. Like your multiplication can be seen as just like a glorified version of addition. So 2 times 5 is basically like add 2 to itself 5 times, and we get 10. Well, a power is like the same thing, but it's like a glorified multiplication. So 2 to the power 5 is 2 times itself 5 times. And if you calculate that out, it will come out to 32. So that's basically what a power is. It's like you have your base, in this case being 2, and you have your exponent, which is 5 in this case. And it means take that base, multiply it by itself that many times, the exponent. So in this case, 2 times by itself 5 times. And we can use that to come up with certain laws that allow us to simplify things. So say if we have something like this, how could we perhaps bring that together into just one calculation rather than, two exponents? Well, you see 2 to the power 4 is just 2 times itself 4 times. 2 to the power 3 is 2 times itself 3 times. Well, this is just a long multiplication, as in there's just many digits all multiplying each other. So if we just lose the brackets, you can see this is 2 times itself 7 times. So 2 to the power 7. And you might be able to notice there that 7 is basically 3 plus 4. And when you have something like this will always happen. So if we take something like this with much bigger digits, we can see it's going to essentially become this. The powers are going to add together and we get 2 to the 76. But something really important to mention here is it's only if the bases are the same. So here, the bases were both 2, but if we have 2 and a 3, in this case, it won't be equal to this. You can't combine them. Nor is it going to be equal to this. If the bases are different, then that's it. You just have to stay as it is. You can't simplify that. So that's just something to bear in mind. So let's look at, say, something like this. If you have a power and then you take to another power, what's going to happen there? Again, we can just use the very definition of what powers are. So here we know 3 to the power 2 is 3 times 3. And then we're taking that 3 times 3 and multiplying that by itself 4 times. And again, this is just a whole bunch of multiplication. We can just lose the brackets and see how many threes we've got here. This is, 8 threes multiplying each other. So that's 3 to the power 8. And again, you might notice a pattern between the powers. I mean, this is what math is. It's all about patterns. 2 times 4 gets you 8. And this is, something that will always happen. So if we take bigger powers like this, 3 to the 12 to the power 5, it's going to become 3 to the 12 times 5, which is 3 to the 60. Very large number, that. Um, right. And a couple of other powers to be mindful of is, say, if you have a negative power, what does that mean? Negative power means to simply take the reciprocal, which is something like this. So if it's a whole number, so 1 to the negative to the power negative 2 is simply going to be 1 over 6 to the positive 2. If it's a fraction that's been taken to a negative power, then it's going to flip the fraction. So 3 over 2 would become 2 over 3. That's what it means to take the reciprocal of a number. So that's what the negative bit is. So you can basically flip it like that, and then you lose the negative part. Or you have like a fractional power like this. Now, the numerator with that fraction, the number on top, in this case, the 1, is just your regular power. So we're doing 6 to the power 1 here, doesn't change anything. But the denominator the number on the bottom, that's the 2, means to do essentially the opposite of a power, which in this case is a root. So in this case, we're taking the second root, or sometimes the square root. We normally don't include the 2 there if it's just the second root. We just include that number if we're doing higher roots. So that leads us on nicely to the next topic, which is roots and surds. So how do we deal with roots? First of all, you want to be familiar with certain numbers. Like here, we have a sequence of square numbers, which are basically 1 squared, 2 squared, 3 squared, 4 squared. And you can see that's going to be 1, 4, 9, 16, and so on. You want to be familiar with these numbers, but only up to about 144. You see beyond there, obviously they're going to continue on forever, but it's only really up to 144 you really need to be familiar with. And same thing with cube numbers. So this is 1 cube, 2 cube, 3 cubed. So that's going to be 1, 8, 27, and so on. Only up to about 125. Just those few numbers you can be familiar with. Normally you won't get asked something with much larger numbers, unless you had a calculator, in which case it's fine. The calculator can do the job for you. So say if we're trying to do the second root of 81, which is, okay, just the square root. We don't have to include the 2. Well, if we spot that 81 is basically 9 times 9. And when you take, the second root, you're basically asking what times itself twice will get 81. So the answer is going to be 9. Or, and this is important, plus or minus 9. Because, like what we saw earlier with negative numbers, if you have two negatives multiplying each other, it comes positive. So here we see 9 times 9 gets 81. but also minus 9 times minus 9 gets 81. So that's why you get plus or minus. There's two possible answers. Um, and then we have things like cube roots. Say if we do the cube root of 125, or if we can spot that 125 is 5 times 5 times 5, then the cube root, basically what times itself 3 times, is going to get 125. Well, we know that's going to be 5. But in this case, it will only be 5, positive 5, because you see, if you did this with negative 5, it will come up to minus 125, not positive. Um, and another thing is you do get two other roots, because that's the thing. When you take a root of something, say the second root, you get two answers. If you do the third root, you do get three answers, and so on and so forth. Um, but these other answers are actually part of what are known as complex numbers, which is beyond GCSE level. You only learn about that at A level, so we don't have to worry about those. In with what you'd be working with, mostly square roots and cube roots, and for even roots, you'll get two answers. For odd roots, you'll get one answer. Um, we can do the same thing with, say, the fourth root. You're probably not likely to encounter this too much, but it's the same logic. You see what times itself 4 times to get 16, and it's 2. But again, it's plus or minus 2. Like I said, even roots will produce two answers for you because you've got positive and a negative. But again, you get two other roots, which are like these complex numbers that you don't have to worry about. But there you go. That's your four answers you get. Um, Right, so let's take a look at surds. So surds is a way of simplifying roots when we want to leave an answer as a root, because when you take the square root of a number, like say 48 here, and it's not the square root of a square number, then you're not going to get an integer answer. And if you don't get an integer, what you are actually getting is an irrational number, which is a number like this that has an infinite decimal expansion that just goes on forever. So you see 6 point and then just infinite digits that never repeat. So you have to stop it at some point. And by doing that, you you're going to lose accuracy. So sometimes we want to leave it as just the square root, but we want to simplify it a bit. So what we could do is things like this. If we notice that 48 is 3 times 16, and 16 is a square number, isn't it? We can actually split those up. We'll see why that works in a second. Um, And so we can then square root the 16, which becomes 4. So we've got root 3 times 4, which we then put like this, where we just put them directly next to each other, 4 root 3. And that when they're right next to each other, like that implies, multiplication. You'll see a lot more of this when we go into algebra. Um, and say if we had like a calculation like this, again, using this third format, we can simplify things because we don't really want to multiply them together and bring them together into one root like this, because then we're getting the square root of 3600, which is quite a big number. Perhaps you might know how to square root that, or perhaps not. Instead, what we want to do is maybe split each one up individually. And you can see we can bring out 36 and 72 and 25 from the 50, which are both square numbers. So we can simplify that. The root 36, root 25 makes 6 and 5. So we multiply them together. And then we've got the two root 2's left over, which is handy because root 2 times root 2 is going to be root 2 squared. And if you're doing the square of a square root, it's going to cancel out. So it's just basically going to be 2. So we have 30 times 2, which is 60. But one thing to be aware of is if you're adding 2 like this, that's not going to be equal to this. You can't combine them together. It only works with multiplication and division. And again, we'll see why that is in a sec. So what we do, again, simplify each one individually, try and break out those square numbers. And here we can see we can get 45 and 49, 25, sorry, and 49. And so we get 5 root 5 plus 7 root 5. And you see when the roots are the same here, we can actually bring those together to get 12 root 5. Because if we've got 5 lots of root 5 plus 7 lots of root 5, it makes sense that would come together to be 12 lots of root 5. But we'll see a bit more of that like when we do algebra. Maybe that'll make more sense. So we're going to take a look at standard form now. So like I said, this is how we deal with very large, very small numbers. So if you have like a number like this, quite a big number, how can we put that in a more concise form? Well, notice that you have the decimal point there at the end of the number. Um, that's where it essentially is for integers, and you can imagine that being 0.000 like we saw in long division. But the reason why we do that is because what we want to do is divide by a 10 over and over again. Because what that essentially does is it moves the decimal point. because, or shifting all the digits. This is a handy way of doing, division by 10. And so we'll keep dividing by 10. So we're taking out those factors of 10 and we just count up how many times do we have to move this across until we can get to a number between 1 and 10. And so we just keep going. And here we get to 145. Next, we get to 14.5. And then finally, we get to 1.45, which is a number between 1 and 10. So that's all good. So we see we took out 10 factors, 8 factors of 10. And so that's 10 to the power 8, isn't it? 10 times 10 times 10, 8 times 10 to the power 8. Another way you could see of it is keeping the decimal point still and seeing how many place values you have to move all your digits along in order to get to a number between 1 and 10 again. And same thing, you're going to see it's going to be 8. And so finally, we can put the number like this. So we've got that 1.45, and we just bring our factors of 10 back in. So it's still the same number, but we put it like this, which you can see is a bit more concise. And this is not a particularly big number to begin with, but when you have really big numbers, like say in astronomy, where you're dealing with like the size of the universe or something, this is really handy. So you don't have to write really long numbers. You can put them in this nice concise form. And we can do the same thing with really small numbers like this. Uh, Same thing again. You see how far you have to shift that decimal point or the digits in order to get to a number between 1 and 10. In this case, we can bring it to 4.6. And again, we're moving it 8 places, but we're not going to get 10 to the 8. We're going to get 10 to the minus 8, which remember is taking the reciprocal. It's like dividing by 10 to the 8. And so if we put this as standard form, it'll be like this. 4.6, not 4.6 divided by 10 to the 8, but we put it as 4.6 times by 10 to the negative 8. That's the standard form that we put it in. And yeah, so just be mindful of that. If you're doing a really small number, the power is going to be negative because you're dividing down to a small number rather than multiplying up to a big number. Right, and so, okay, how do we do a bit of arithmetic with standard form? Well, it's not too bad because we've just got a bunch of numbers here multiplying each other. So we could lose the brackets and shift things around a little bit like this, and then put the brackets back in if you want. And so you see we've got these two just numbers part that we're multiplying, and then we have the two powers of 10 that we're multiplying. So 5.2 times 3.9, we'd have to multiply that um, through our long multiplication or with a calculator. But I know we haven't done long multiplication of decimals yet, but we'll see soon enough how to do that. And then the powers, again, when we multiply them together like this with the same base, you see the powers are going to add together. So you get 24 plus minus 13. So that's going to be minus 13 and comes to 10 to the 11. But this is still not in standard form because remember that first number has to be a number between 1 and 10. So we have to take another factor of 10 out of that. So 20.28 becomes 2.028. And we add that extra factor of 10 to the collection of tens that we have there. So if you're not so confident with those decimal parts there, with the decimal points, don't worry, we'll be taking more a look at that in, I think our next session, on proportions. So finally, let's finish up with order of operations. So this is when we've got many operations going on, we need to know what order to do them in. Well, we have a little acronym for remembering this, sometimes known as BIDMAS, or I call BIRDMAS, for completion. So if we break this down and see what exactly that means, it means brackets, indices, and roots, division, multiplication, addition, and subtraction. And you see each of those pairs, they come on the same level. And so if we take an example like this, say 3 times 4 divided by 2, it doesn't matter what order we're doing those in because those operations are on the same level, division, multiplication level. And so you see here, where I calculate them in different orders, and you see the answer comes out the same, and it's fine. But you see, if we have something like this, we've got addition, we've got multiplication, and we've got power. We need to make sure we're using the BIRDMAS here. So you do brackets first. So brackets, whatever's in brackets, you treat like its own little expression. You deal with that first. You again using the remaining of the BIRDMAS, and then carry on with the rest. But we don't have brackets here, so that's fine. So you see here, I'm showing a couple examples of like if I change up the order in which we do things, you can see you get different answers, and actually both of these answers are wrong. What we need to do is this, and that's the correct answer because okay, powers, like the indices, comes first. So we do 5 squared, which is 25. Then the next one down the order is the multiplication. So we do 2 times 25 gets 50. And then finally we do the addition. So 3 plus 50 gets 53. So that's the order in which we do it. And this is more just a convention more than anything else. It's just something that mathematicians agree to so that, I could look at your work, you could look at my work, and we can understand what each other are doing. Like if we had different operations, like different order, it wouldn't make sense. It'd be like me, speaking English right now, but all the words mean something different. Like we wouldn't be able to communicate. So that's why we do this. Um, and wanted to mention quickly about distributive properties I mentioned earlier. So you see something like here, like multiplication um, can distribute over addition. So what I mean by that is, you see this is basically 3 times 6, isn't it? So we get, it's basically 3 added to itself 6 times. But you could also see this as 3 added to itself 4 times plus 3 added to itself 2 times. And so it's 3 times 4 plus 3 times 2. And so that's what I mean. So you see, you do 3 times by 4 plus 2 in brackets there. We can split that up into 3 times 4 and 3 times 2, and it works. And the same thing works with roots and like multiplication and division. If I take this to the third power, it's the same thing as doing 5 times 2 times itself 3 times. But if I put some brackets in there like that, um, yeah, so that's 5 times 2 times itself 3 times, yeah. But yeah, I could easily swap it around like this, and you see it's 5 times itself 3 times and 2 times itself 3 times as well. So you see there, that power distributes over each of the numbers inside when it comes to multiplication. But it doesn't jump 2 levels on the bird mass. So here, 5 plus 2 squared is not going to be the same thing as 5 squared plus 2 squared. And I would encourage you to work that out. Work out both sides of that there, and you'll see that they don't come out the same. So, and the same thing if you have something more complicated like this, it wouldn't be this. Like, even though, yeah, it distributes over multiplication, you can't split at the multiplication point here because you've got that addition there. So that one addition kind of ruins it for everything inside the root there. So that's something to be mindful of. If everything inside that root was multiplying, then we could split it up, but we can't here because that addition. So that's how that works, which will be a lot more important when we come to algebra. Um, so that's it. That's the end of the first lesson. I know there was a lot in the first lesson, but there was a lot of different topics we had to cover there. So we always like to finish up with a did you know here, which is beyond GCSE level, but it's just more for your any interest. So we was looking at base 10 count system, but there are other types of count system, like say binary, which is what computers use, which is base 2, where you just have 2 digits 0 and 1, and we count from there. So rather than doing units, tens, hundreds, thousands, we do powers of 2. So it's units, twos, fours, eights, 16s, and so on. So in decimal, we'd have the number 13 like this. That same number in binary would look like this. So I'd encourage you to take a look at that and see if you can work out why that would look like that in binary when you see it's increasing powers of 2 rather than powers of 100. But yeah, leave it there. Here's the takeaways for today's lesson. I encourage you to pause here and take a look at this. Make sure you understand everything before moving on. Next time, we're going to be taking a look at proportions. So I will see you there.